Mom, I'm busy now for the next 2 hours. I'm busy now for the next 2 hours. No, it's okay. I'll take it in the middle. Don't worry about it. Hello. So hopefully, can everyone hear me over YouTube? Latency. So I'm not streaming from Discord because Discord had so many problems last time, every single time, that I'm not gonna bother doing this. Okay, whenever I speak from here, it'll echo through YouTube, but I'm gonna tell everyone here. I'm doing it through YouTube because Discord just keeps breaking when there's too many people and there's too many people in this one stream. Most of the time, people can't see it, and most of the time, it just keeps breaking, and then the audio falls off. There's a whole bunch of issues with it. And it's been the same issue with all the sessions, so I just don't want to do that. And you can go on YouTube; it's easier. And also, it saves on YouTube automatically afterwards, like it records it. No, so yeah, you don't have to stay in the VC if I'm live on YouTube, obviously. But I mean, if you want to say something to me, I'll have the VC open so that when someone pops in, they can turn on their camera and do it. It's cracking on my YouTube. Yeah, so no one has to join the VC. I'll look mainly at the YouTube chat for now. So that's people who are obviously listening to YouTube because I'm muted on the Discord. If anyone has anything to say to me, they can unmute themselves on the Discord and they can pop in the Discord VC, unmute themselves, say something to me, and then I'll continue. All right? That seems like the best solution right now. I'm going to stay in the Discord VC. I'll be on YouTube as well. I'll check back on the YouTube live chat every once in a while if anyone has any questions. But yeah, this seems to be the best solution for me right now. Let me see. Yeah, well, it's okay. Good connection. That's good enough. So hopefully everyone can hear me well, and yeah. So I'll give it another 2 minutes, and then I'll start the session. Oh my god, 21 viewers. Jeez, okay. I should just on Twitch, and then I'd get like more. I might get affiliate, real quick. Okay. I think that's enough viewers for me to just begin. So plug in my tablet and I'll begin. So this is topic 6+7, topic 6 and 7, and 16 and 17, the additional HL content. I'll say what's HL, what's SL throughout the time. So the slides they're made by me and they're made by Dice, Ventricle, who just did the biology session. These were made for the November 20 session, but I mean, I could just use the same ones because I literally made the same thing. So yeah, some of the slides are mine, some of the slides are hers. But I'm gonna be doing the session alone. So yeah. Okay. Let's start off with topic 6. So that's rates. Topic 6 and 7 to me in my head they kind of just blend together as the same topic. Because they're just rates, equilibriums. It all kind of just gets together in my head. But yeah, topic 6. This is SL content. So we're just gonna look at like simple rates and like the things that you need to know in order for rates. Which is again the thing I'm gonna do a bare bones explanation of everything that's needed. Right. I'm not going to go into detail or go into too many things regarding the things. I don't want to waste time. I'll go through things quick, and that's exactly what's needed for your session. So that I mean, if you don't notice that you didn't that there's something here you don't know at all, then now that's your cue to take that and then go and study that. This is not like a comprehensive explanation of everything, more so exactly what it is called. It's a revision session where we revise and make sure that you have everything with you. What I'm going to try before I continue is I'm going to try and see if I can open the pop-out chat like this, and then I will do that so I can see anyone saying anything in the chat at the same time. Okay. So now I can look at the chat at the same time, so if anyone wants to say anything to me, I have the chat open. Okay. So first thing, units of concentration. That's important. It's topic 1 and 2, topic 1 content, but units of concentration is moles per dm cubed. Dm cubed is just the same as like moles per liter, right? So dm cubed is a liter. I think it's important to remember what dm cubed is and what cm cubed are. So that kind of unit stuff is something that could really mess you up if you're not paying close attention. So for example, if I were doing, so this is how I remember it. I remember dm cubed is always a liter. I remember that centimeters cubed is always a milliliter, right? And then based off of that, I convert between them. So if I have like dm cubed and cm cubed somewhere, I want to convert so I can get them the right units. I don't bother with like understanding and trying to remember cm is 1,000 more dm. I just remember liter and milliliter and do it like that. I find that easier for myself. So I would recommend that as well. It keeps it, because everyone knows liters and milliliters. No one's gonna forget that. Yeah, and sometimes you might also end up with you might also want to use meters cubed, which is 1,000 liters. So 1,000 liters. And you may have that, but very unlikely, very unlikely. And then there's change in concentration per unit time. So that's what the actual reaction rate is. So reaction rate is when there's a change in concentration over time. Actually, you know what? Is there a way for me to write on this thing on itself? Like tools, insert. No, I don't think there is. That's all right. Then changing concentration per unit time. So that's moles per, that's the concentration per unit time. So that would just be, I can pop that up as well. That would be moles per dm -3. So that's the concentration per unit time. And this could be s to -1, right? It could be per unit time, so per second. It could also be per minute. So I've seen various applications. It could be minute or second. For really slow reactions, they will not avoid having it for maybe an hour or maybe having like a year. There's all it could use any kind of time coordination, right? So what you should be comfortable with is understanding that it's per any unit time, and you should be comfortable in switching. So for example, if you had like 1 mole per dm negative 3 per minute, then you know what it is going to be for an hour, because it's going to be 60 moles dm cubed per hour. So you should be comfortable with those kinds of conversions as well. Molar ratios, yeah. So and then give me a second. Wait. Yeah. So the actual rate expression itself. Actually, 1 second. Wait. So, oh yeah. So there's no rate. Can someone confirm this for me? There's no rate expression for SL, right? Someone can put it in the live chat. I don't know. I mean, I don't remember. I don't think there's any rate expression for SL, so it's fine. Oh, yeah, no, good, thanks. I got a response. Anyway, so yeah, let's continue. Then molar ratios and stoichiometry. So whenever you have like a certain equation and there's a certain like rate happening, the rates of each of the reactants or products will be proportional according to whatever their molar ratios say. So for example, so again, this is kind of obvious for anyone who's for HL, this is just obvious, but for SL, I guess they only want a simpler understanding. So for example, I think I could come up with like 2H2 plus O2 gives me 2H2O, right? So if I find out, right, that the O2 is being used up at a rate of say 3 moles dm negative 3 per second, right? Then I can equivalently say that the hydrogen gas is being used up at a rate of 6 moles dm negative 3 per second. So I could that is how it works for all stoichiometry, right? So that's another connection, and then obviously you'd also figure out that because the molar ratio is the same, it'd be multiplied by 2. It'd be 6 moles dm negative 3 s negative 1 for the right hand side for H2O. So those are the ways you could do that. Next is initial, instantaneous, and average rate. So here I got a little diagram here. So as you can see, the instantaneous rate. So there's 3 types of rates: so initial rate, instantaneous, and average. Initial rate is the rate as the reaction just immediately starts off, right? Then instantaneous rate is the rate at any given point. And average rate is the total rate of the reaction over a given period of time. The initial rate is an instantaneous rate. It's an instantaneous rate at time 0. So for example, if we pop up over here, you can see what an instantaneous rate looks like. It's just the slope of a line demonstrating reaction progress, and you should be able to find out how to look at the change in the concentration over the change in the time for whatever line you're looking at. So that's some simple mathematics you're going to have to be able to do. They could ask you for the instantaneous rate at many points, so you should also be comfortable with using a ruler to try and find the tangent lines to a curve. And then for initial rate, obviously it's at time 0, so you also want to find the tangent line at time 0 if you wanted to find the initial rate, and that would be able to give you the accurate initial rate value as well. Average rate, for this reaction, for example, average rate is by literally just taking 2 points on whatever curve you're looking at. So for example, if I said what's the average rate over the time 40 to 100 seconds, I would take, I'm going to pop over to a screen snip again. If I were to take from 40 to 60, 40 to 100, I would take this point over here, actually, color, 40 to 100, that's the line I would use. Actually, that's not the line I'd use because that's a really badly drawn line. I have a ruler here. Let me see if I know how to use this ruler. there, there. See, looks great. Okay. The ruler. So that's my line between the 2 points. As you can tell, it's not exactly accurate because it's not really. Actually, in this case, it looks kind of accurate, but it isn't accurate, obviously, because it's not like what does it even mean? Obviously, the rate of change was different at 40 and different at 100 and different at all points in between it. So clearly, this is not accurate. It's just a rough estimate, and that's what the average rate is. So, but actually, the good thing about an average rate, it's really easy to calculate. Like all you have to do is whatever 2 points you picked, right? You just have to find the change in concentration between them and divide it by the change in time between them. And they could ask you for any possible combinations for what you want to find for average rate, right? So they could ask like 40 to 100, or they could do like 0 to 160 or anything. Okay, I love how I got some in the chat. I forgot to find incident rate is bigger or smaller difference between numbers better to find the rate without making mistakes. Let me think about that for 1 second. It doesn't make a difference. It doesn't make a difference what you do. If you take a ruler, right, and you've put a line next to it, right, and you find and then you draw that ruler's line, right, whether you choose big numbers or small numbers, your value will be exactly the same. It'll be the same. And the reason it'll be exactly the same is because what you're doing essentially is finding the slope of that line. Whatever numbers or points you choose on that line, the slope will always be the same. However, it is important to note that if we are taking into account uncertainty, right, like the uncertainty of the measurements that you're using for time or the measurements you're using for concentration, then yes, a bigger value is actually better because what it does is it reduces the percent uncertainty of your of the values. However, that's not something I've ever seen be assessed, and whether you use bigger or smaller doesn't matter. What actually matters is whether you're actually passing through a correct point. So your aim whenever you're trying to find a tangent is that the line actually passes through points, because if it just passes through no points on the actual graph or grid, then you'll have a really hard time trying to figure out what the slope of that line is. So avoid that. You don't have to worry about that. Just make sure that whatever line you draw is going through some points. And as far as I know, whenever they ask you to do this in a test, there's a lot of leeway, right? Like there's a massive leeway for the slope. Like they could say, accept any value from this to this. And so from what I see, if they ask you like something like find the initial rate, right? Or find the instantaneous rate at this point, that would be like somewhere between 2 to 3 marks for the question, right? Of which 1 or 2 of those marks are going to be your application of the skills, not your actual answer. So if you are able to show that you understand that in order to find rates, you need to find the change in concentration over the change in time, that already gives you a mark. If you just show that you did a calculation for that, that might give you another mark. And then if you get the right answer, maybe that's another mark, right? Something like that's what could happen, right? So more realistically, probably 2 marks. If you end up messing up the slope number, you lose 1 mark. But if you end up doing the slope like calculation, like show the calculation correctly, as in like there's a change in concentration over change in time, you might get the other mark. So there's always that for you, right? You don't have to worry about missing out there. You'll get at least 1 mark, which is better than none. Okay, so there's a lot of experimental methods you can use to determine the rate of reaction. Again, so SL doesn't go into too much detail about this, but these are some techniques you're gonna need to know, because what ends up happening is what they could ask you is they could just give you random equations, and what you need to know is how to solve like they'll ask you, how can I measure the rate of this reaction progressing, right? So these are a couple of experimental methods that exist. So I'll explain them. There's mass loss with a cotton blocking flask. So what you could do is have a reaction in a Erlenmeyer flask. That's a regular flask. And what they do is they cover the top with cotton so that any of the liquids inside, any of the solids inside don't fly out or burst outside. But what can pass through is all of the gas, right? So what you could do is you can measure the Erlenmeyer's flask's mass before the cotton, before the reaction, and then you can run the reaction, and then you can measure the mass as the reaction progresses. And whatever that mass is gas being lost from the top with whatever. If the mass reduces, it's gas being lost to the carbon blocking fast. So an example for this kind of reaction would be, you could do something like, I honestly, I blank, but anything that's forming gases could do something like this, as long as you have like a bunch of other aqueous liquid products. So like, I mean, the first thing I can think of is like electrolysis of water. It's stupid, but at the end of the day, you're gonna have like a bunch of gas coming out. So that could be one of the things you're using. Okay. Before I move on, I'll just look at the question. Wait, what was that thing in slide 5 about taking the rate as b because its stoichiometric coefficient is 1? Let me have a look. Let me think. See, I didn't make this slide, so I don't know, but give me a minute. I don't think it's relevant right now. I think this is something I'm going to go over later anyways. Yeah, okay. So I'll set you. I'm getting right back to you. I'm going through the methods. I'll mention that as well. Then a gas syringe, that's an easy one. Oh, I got a good reaction. You could have lactic acid with a carbonate or something. That's going to give out carbon dioxide gas. You can measure the reaction progress of that with a gas syringe, right? It's a gas syringe is a really good way to do it. So that's a good way to measure gas. You can also do gas collection over water. So what you could do is you can actually run a tube from your flask into like a bucket of water, like a beaker of water, and then put an upside down test tube or collection tube into the water. And as the gas comes out of the tube, it collects inside of the test tube or the whatever beaker you have. And that's another way for you to collect. That's another way for you to collect gas and measure how much is there. That is a method that, to be honest, I have never seen them use it. Gas syringe seems okay. So far, I think the gas syringe is the safest one to put as an answer. Mass loss of the carbon blocking fast and gas collection over water. I have never seen them actually give questions related to that. Maybe it's a paper 3 thing, but definitely not a paper 2 thing. But again, it's just one. This is some methods you should know in general, so that you're better able to solve questions that are a little more critical thinking based. So yeah, one more thing. I'll just finish this, then I'll answer the question with God of Platinum's put up. Obscuring cross is a good one, because what happens sometimes, you have reactions where there's a precipitate forming. So for example, you could have a copper chloride solution where you put in a piece of aluminum metal, right? If you put a piece of aluminum metal in copper chloride solution, the aluminum is more reactive than the copper. It's going to displace the copper in the reaction, and the copper is going to form as solid in the reaction. That solid is going to precipitate to the bottom. So what you could do is have a cross at the bottom and measure how long it takes for that cross to become obscured by the copper formation in the beaker, right? Because there's copper powder falling onto making the reaction a little murky. Then you can also look at color, right? So for example, if you're looking at organic chemistry, again, I don't think this is SL does not learn this, but HL does. There is the reaction between, I think, if you're oxidizing an alcohol into an aldehyde or a carboxylic acid, you have to use dichromate, potassium dichromate or potassium permanganate. If you're using potassium permanganate, it's going to go from purple to colorless. If you're using dichromate, it's going to go from orange to green. So that's another way you can measure. So how fast does that color happen? Alternatively, the best way to measure color changes is with a colorimeter. So it's something that like tells you the exact wavelength of light that a color is, because obviously it's really like inaccurate to say it went from orange to green in 10 seconds. Like you should say like, okay, it went from this, how the wavelength is changing over time. So that's using a colorimeter. The most common reason for using color is permanganate, because they expect you to know that that's purple. And definitely it could be the example with oxidation of alcohols. And additionally, it could also be, and the most common one is iodine, because iodine is brown. And I think the clock reaction is kind of in the syllabus. I mean, it's not in the syllabus, one of the required practicals, but it's not assessed anymore because we don't have paper 3. But it's still something interesting. It's something that comes up in paper 2s very often. You need to know that iodine is brown, permanganate is purple, and that dichromate is orange goes to green in reaction. Oh, and the final one is the digital meter. So that's using pH meters or something like that, right? You just stick a pH meter in there. There's other meters like colorimeter, there's other kinds of, different kinds of digital meters you can use. Digital meters is usually the most accurate one. So for example, in the test, if they ask you like, what is a better way for this person to measure the rate? Or so for example, they could have a titration or something, and in that titration, you could have a going from a you want to try and find the equivalence point of that titration, right? And we might want to use an indicator. So you could use an indicator, that's fair. But sometimes it's better if you just use a digital meter. And if you did use a digital meter, it makes it a lot easier to just immediately tell what the equivalence point is, because you know when the pH starts like flattening out as you add stuff to it. And so you could write is you could say this experiment could become more accurate if you did use a digital meter. Okay, got a platinum. Are we covering 1 over t x-axis, L and ky axis curve? I don't understand what's going on in this question. Yep, of course. Yeah, I think that's HL content. That's also in our Arrhenius equations. That's topic 7. No, it's later. It's in the HL content. I'll go over that. So yeah, monitoring reaction rate. So for example, this is some examples of reactions that could come. So if you have magnesium, okay, so there's a bunch of cool stuff here, which I should have realized. One of the ones that I really forgot to put in over here. Calorimeter, right? Temperature measurements. One of the best ways. One of the most common ways they put up in an exam is calorimetry for this. Monitoring reaction rates. Yeah, look, you know what? I'll share the slides right now. Give me a minute. Wait. 1 second. I doxed people. I doxed a lot of people there. That was bad. It's okay. Okay. Let me just pin that as well. Sorry. Okay. Here's some reaction rates you can have. You could have Mg plus HCl. That gives you magnesium chloride and hydrogen gas. That's volume of gas produced. You could have a acid-base reaction, which is using exothermic, which is finding the heat released because it's exothermic. This is a super common one that come in an exam. And you know what? Another thing that could really come in an exam very often is they won't just ask you sodium hydroxide with a hydrochloric acid. They'll compare 2 different ones. So I was just doing a paper yesterday. I think it was the November 2017 paper where they discussed if you have sodium hydroxide with hydrochloric acid, and then they compared it with a graph for sodium hydroxide with ethanoic acid, right, a weak acid. And then there's also different reaction rates according to that, right? Because if you have a weak acid, it's going to take more energy to first try and ionize that acid, and then to go ahead to try and actually have an acid-base reaction. So it's less exothermic, and the reaction rate is slowed down. And that can show in the graph, and it's important for you to be able to explain that as well. Again, that's topic 8 material, but that's another thing to keep in mind with these acid-base reactions. They could ask you the difference between weak and strong acids and how it differs. And then, yeah, there's obscure mark technique. I already gave an example for that earlier, but this is another one. You could have NaCl with silver nitrate. You get sodium nitrate and silver chloride. Silver chloride is a solid, so it precipitates in solution. And then you can use the obscure mark technique. Yeah. Now for collision theory, so the whole point of the only way a reaction can occur, right? Once you give me a minute. Yeah, so I'll just move here and then I'll go back to that slide. So in order for a chemical reaction to start, the reactants must collide with enough energy. So they must overcome the attractive forces between the molecules in order to actually, so they must overcome they must have enough energy to collide with one another, and they must collide with the correct orientation. So this is pretty, that's kind of the point of how you make a collision. So there's 2 things you could increase. You could increase the correct orientation, so have more orientations for it to attack, or you could make sure that the reactants have more energy, or you can make sure the reactants have more energy, which is like increasing the temperature, or you can try and introduce a catalyst which will reduce the amount of energy even needed in order for it to think. So the amount of energy needed is the activation energy, right? So it's written in big capital letters, bolded right there. And another interesting thing to remember is the correct orientation things matter. The more complex a molecule gets, the more difficult it is for a reaction to happen. So for example, in organic chemistry, if you have like an SN2 mechanism, an SN1 mechanism, those are relatively slower than if you just had something like a sodium hydroxide with hydrochloric acid, right? Because the hydrochloric acid, sodium hydroxide is a much simpler reactions happening, but an SN2 mechanism, something that has to have a very correct orientation to attack, and and that's what actually increases complexity of the reaction. And later for HL, we'll see how that affects it. But all SL needs to know is the general connections for collision theory, right? And the idea that you need to have enough energy, the activation energy, and you need to have correct orientation. And so that's how it is. So you can also, another interesting, so the main things that actually affect the collision theory, the amount that can happen, is you have concentration and pressure, right? So the concentration will automatically increase the amount of collisions per second. And because the concentration means that there's more collisions in one space, which means that there's going to be more collisions per second, or more collisions per unit time, which is going to result in a faster rate of reaction. Same thing with pressure. If you increase the pressure of a reaction, usually what that does is it reduces the volume, or you're having particles that are moving faster because either volume has to reduce in order for it to be more concentrated, or the temperature has to increase, which means they have more energy as kinetic energy particles. So in that sense, you have more energy. Yep. Yes, again, so Ben Min just pointed out in the chat, doesn't Arrhenius constant take account for the collision orientation? Yep, that's correct. The Arrhenius constant does it. That's the A right in the front. And I won't go over that right now. Again, I said I'll go that for HL, but yeah, that's correct. But SL does not need to know that. It's not needed. Then the other interesting thing is surface area matters a lot for the collision. And so solids have like almost negligible surface area. It's basically useless. Like solutions are just somewhere in the middle, like random solutions. But gases have the fastest reaction rates, right? Because they're just all over each other, just mingling all through, right? Solids are just like stuck next to each other. You stick two solids together, they're not going to react. So yeah, but then you could also help a solid react more faster if you powdered it, right? Because you're increasing the surface area of that solid. That's another thing you gotta really keep in mind if you don't know it already. They might ask a lot of times in the tests, how could you increase rate of reaction in different ways? You could say, okay, maybe pressure increases, concentration increases, maybe whatever solute you're adding, you can powder it, maybe you can bubble it through, like different things like that. There's a lot of ways. So like if you wanted to increase the oxidation of an aqueous solution, instead of just leaving it out there for the oxygen to react with the surface of the beaker, you can also bubble the oxygen through. So there's all these different ways that you can try and increase rates of reaction. And most of them are quite obvious, right? And I think this goes into a little more broader idea of what we're doing in chemistry in general. You will perform better in this topic and in topic 5, for example, or topic 1, if you have more real world practical experience with your IAs and with actual real life practicals. Now, knowing that there was COVID, right, that you didn't get that kind of experience. The reason I know all of these things, and just off the top of my head, is because I watched Nile Red videos. So here's a plug and a shout out. Please watch Nile Red videos. They like if it's entertaining, right? So but it also counts as studying, right? Because it's chemistry. So if you're like preparing for exams, you just want to watch something really chill to watch, just watch one of his videos. His videos go into, sometimes they have intersections with IB content, and usually most of the time they have a lot of very interesting ways to like experimental methods and things. And I think it'll help you a lot with. I think it'll help you guys a lot with remembering these things and developing some critical thinking when it comes to chemistry. Right? His videos are great. I think you'll enjoy them. So please go do that as well. If you find it difficult trying to come up with these, if someone asks you like how to fix this, you're like, what the fuck, right? Those kind of situations. So yeah, now I'll put it in chat 1 second. Actually, you know what I'm gonna do? I'm gonna do one. Let me just open up his YouTube channel. No, that's the wrong one. That's definitely not it. So Nile Red is really good, right? That's like really entertaining videos. But the other one I would definitely recommend get going is Mr. M for something like this. Yeah, Mr. M for Chem. This guy, absolute legend. But he can do better than Nile Red would never do any day. I mean, because he's an IB teacher. He's also on the server, by the way. So Nile Red is what I would just generally like look at just for fun. Mr. M for Chem gives you specific advice for IB. And it's really, really, really good. He sort of saved my day, made it a lot better than it could normally be. Yeah, so look at these two YouTubers; they're really good. I would strongly recommend. Actually, I'm gonna pop these. I'm gonna pin these in the chat. Okay, so one second. The reason audio might be breaking right now is because the I was just using my laptop and my microphone is right where my mouse pad is. So sometimes when I like I graze against the microphone and it cracks and you won't be able to hear. But it's fine. It's all fine now. I'll try and avoid that. Finally, there's Boltzmann diagrams. So again, this is something I hopefully everyone already knows. But the important things to know about Boltzmann diagrams is you have your curves. So this diagram actually says most of the things. So the Boltzmann diagram basically indicates the number of collisions, the number of collisions at different energies, right? And what you're trying to maximize, right, is you're trying to maximize so in order to increase your rate of reaction or to have a reaction happen, you're trying to make sure that you have as many collisions at a higher rate of high energy. At what point of energy higher? Higher than the activation energy. And whatever fraction, again, under the curve is above the activation energy, that helps with the rate of reaction, right? This is something very important you need to know how to say, right? If you have whatever fraction under the curve, right? The fraction under the, like whatever fraction, whatever area under the curve above the activation energy, that's important because that's something that mark schemes have. So there's two different changes you can have with the Boltzmann diagram, and two changes which you should be able to draw, label, and explain, because these are things that the IB regularly asks. So for example, in the blue curve, right, that's a lower temperature, and if you have a higher temperature, T2, and you increased it, you would move the Boltzmann diagram in two ways. One, the peak is now lower, okay, and the peak has moved to the right, okay? And in general, towards the right-hand side of the diagram, the red is now higher than the blue, right? That's really important. In the mark scheme, it literally says exactly that. It says needs to have three things. One, the peak is lower. Two, the peak is to the right. Three, it's significantly higher towards the right-hand side of the diagram, right? Those three things are the way you get it immediately. Don't worry about drawing a super cool-looking diagram. All it has to do is meet those two criteria. Meet those three criteria. The second thing is the activation energy. So if you reduce the activation energy, obviously, if you reduce the activation energy, there's going to be more area under the curve because you're moving it to the left, you're getting more area. So that's exactly what that's why the activation energy increases the rate of reaction. If they were to ask you in an exam, why does the activation energy increase the rate of reaction? This kind of diagram is really helpful for you to try and explain that, right? Because you can immediately say, if you reduce the activation energy, there's going to be more collisions with enough collision energy above the activation energy in order to react to actually like progress the reaction in a different way, right? Okay. I have a ping. Is anyone? Oh, not mine. Okay. All right. That's all. There's some more simple theory. Oh, so I already discussed this a little earlier. There's concentration, which impacts rates. So concentration, more particles, more collisions. Volume, less space, more collisions. Temperature, more kinetic energy, so more particles with the required activation energy. I don't know what Gauda-Platt. So Gauda-Plattman's saying, so rule of thumb is positive skew, normal distribution when drawing this stuff. No, not really. It honestly doesn't really matter how you draw it. Again, yeah, so this is my point. It doesn't matter how you draw it, what it looks like. All that matters, right, is that your peak is lower and to the right when the temperature increases, right? That's what matters. That's what they care about. That's what the 2 marks are for. So it doesn't matter whether you can draw it correctly or if it looks like whatever, right? Like if your like general shape is sort of off, they can't cut marks for that because you haven't done anything wrong according to the mark scheme. So yeah, let's keep going. Temperature, we discussed that. Surface area, again, we discussed that. If there's a smaller size, more surface area, more space for collisions. Then the catalyst, again, we discussed that. So catalyst and temperature, please refer back to your Boltzmann diagram, always, right? That will help you do two things. One, it will help you to actually be able to explain these two effects in a short answer question much better. And it will also help you remember what the Boltzmann diagram is. So if they ever ask you to draw one, you immediately know what to say and immediately know what to do. So now let's pop on into the math. So this is all HL stuff now. I think all the math here is all HL stuff. So HL is SLs you can pop off for a little bit until I'm heading back into topic 7. But right now this is HL stuff. I think what I could do is I could pop a ping to anyone in the chat. For M21 Chemistry, I'll just ping the role saying we're back going with topic 7. But for now, I'm swapping entirely over to HL. This is all HL content. I will ping again once we're starting with topic 7. So the first thing you gotta know is reaction profiles. So we already covered this in topic 5, and how reaction profiles work, reactants, and then there's products. So in this example, the reactants are higher, the products are lower, and so that means it's let's just for revision's sake, it is an endothermic reaction because actually, one second. No, it's an exothermic reaction because the particles are losing potential energy, which means they're losing energy to the environment around it. But then the interesting thing you got to know is that the activation energy is higher than that. So the activation energy is generally much higher than the reactants or products or whatever they needed. And then after they made it past that activation energy, they go back down to the products. And that's why reactions have to make it past a certain level of activation energy. Let me look back at chat. I think one thing you should mention about catalyst is that it doesn't really decrease EA, just provides another pathway for the reaction, which is a lower EA required for the reaction to take place. Yep, that's correct. I should mention that. Right? A catalyst, right? So okay, we're hopping over here. I was gonna say it over here is because SL doesn't actually. I don't think SL needs to know that. But maybe they do. But this is I had it in my HL slide. So what the catalyst does, right, is it provides an alternate reaction pathway which can then lower activation energy, and that's what you explain in a question. It provides an alternate reaction pathway, and then what that allows you to do is you can have a lower activation energy. So we know how that increased rate of reaction with the Boltzmann diagram, but on a reaction profile, it would reduce the hill it has to get over in order to become a product or whatever it is, right? So yeah. So here's some math, right? So for HLs, first you got to know what your rate expressions are. Let me see. Is the line supposed to start at the origin because there being some specificity regarding where it starts? No, I have never seen any specificity about where it starts. But yeah, I would put it at the origin anyways. That makes sense, right? Like, because if you think about it, right, it has to be 0, 0 because there are no particles, right, which have it can't be any higher than there can't be more than 0 particles that have 0 energy because no particle can have 0 energy. Remember, the kinetic energy particles? Let me think about this. The kinetic energy of particles, right, is measured by temperature, right? And the measurement of temperature we use to describe that is Kelvin, right? But if you had 0 energy, right, that means that you have 0 Kelvin. 0 Kelvin is impossible. We all know this. You can't have absolute 0. It's absolutely impossible. So yeah, you would have to have 0, 0 as your base. There's no other way to do it. That's how I would reason through it. Again, so now we're gonna pop over to rate expression. So rate expressions is there's no per substance rate expression. Again, this is something you should just have in your head, straight up, memorized, right? You have to base this on whatever your rate determining step is. I'm gonna pretend this is my rate determining step because this seems to be my go-to example for now. If this is what your reaction looks like, actually, one second. Would you use either of these? Because they're both pure. No, you would use these. Would you? Why am I getting confused about this? No, of course you would have to look at this, yeah. So if you had this reaction right now, you could have R is equal to K, H2 squared, O2, right? That's your rate equations. You have R, which is your rate expression, K, which is a constant, which has certain units, whatever those units are. And then you have H2 squared, because that's what the coefficient is over here, and O2, right? This is generally only true for when you know for sure that this is the rate determining step, because not every step is a rate determining step. Now, what do I mean by that? Also, no, the pure substance. There's some. Okay, so what does it become a pure? What I think no pure substances means is that you don't put any solids in there, or don't put any pure liquid. So, for example, if you have an aqueous solution, don't you're not going to yeah. So yeah, it depends on the state. So don't put. What is it? What does that affect it again? I think it's the concentration of like water or something. Like if you had H2O on one side, that's what it is. There is a reason where you can't do it. If anyone else knows it, please help me. But yeah, anyways, I'll keep going for now, and I think we can come back to this. Then rate determining step, which is the so there's many steps in a reaction usually. There are, and different steps, right, have different speeds at which they occur. So depending on all of those things, there's different it depends on how. So, and obviously you can have certain steps that are faster than other steps. So there's fast steps, there's slow steps. But the step that overall determines how fast the reaction goes is the slowest step, right? The weakest chain, the weakest link in the chain. The slow step, right? So the slow step is usually your rate determining step. And and usually in questions they'll give you like a series of steps and they'll label them. They'll label them fast, slow, whatever. And the slow step is a rate determining step. That's what you need to remember. And that's the step by which you will make your rate expression from. However, remember, your rate expression can only ever have reactants that are actual reactants, right? Because when you have multiple steps, what usually happens is you have intermediates, or you have like catalysts, or you might have other things. You're only allowed to have reactants. And the way that IB expects you to figure out what the actual thing is that you should be able to go backwards and use the previous equations to try and derive what the connection would be with the original reactants for whatever products you have. So that's another thing you got to remember. It usually isn't quite difficult because they give you, it's very simple to it'll be something like, so for example, there was like NO, right, in my rate expression, and I was like, oh shit, that doesn't exist in the reactants. What they would have is they would have something like this. They would have and this is obviously not true, but they would have like NO2, NO like this, right? And then you can just replace NO with NO2 because there's like this equilibrium thing happening here. Or for example, they could have like 2 NO2 over here, and then in which case you would make it like, you would replace it with NO2 squared or something like that. That's usually what you would end up doing. Okay. How to determine the rate of reaction when the only info I have is fast and slow steps in reaction? Yeah, so if you only have fast and slow steps in reaction, you pick the slow step and you go with that, right? The slowest step is the one. I've never seen them give you more than one slow step. They only give you one. They don't make this hard for you. Because, to be entirely honest, it's not exactly fully accurate what they say most of the time. But for IB's sake, this is how it works and this is how it goes. Next, so we have the rate constant. So essentially the K right in front of it. Now that K is important because you need to be able to find the units of that K, right, at certain times. And I'll explain why. So let's pop. No, so yeah, so catalyst cannot be in the rate expression, okay? Rate expression can only be the actual reactants. Catalyst is not counted as a reactant because it's made and then it gets reproduced at the end of it. Do I have any important things? IB talk and okay, that's fine. Okay, rate expression, no pure substances. What was I looking at? Rate constant. Okay, I'm just going to show you the reaction mechanism pathway for that. How to find the rate constants units. Yeah, the catalyst cannot be in a rate expression. I'm certain of that. Because, again, think about it. A catalyst doesn't even exist. I mean, the catalyst speeds it up, but it's not part of the, I mean, it is part of the reaction, but you can't count it as a part of the reaction. So, no, the catalyst is not affecting it at all. But it does affect the rate by the rate constant. But, okay, let's see. So I'm going to do a whiteboard. So I'm just going to explain how the rate constant defined in units. So R is equal to K, and let's, for this simplicity's sake, let's make it like H2 squared, and then we have O2, right? You need to be able to find the units of the K, right? We know the R is moles dm negative cubed. So instead of using that for now, because it's too long, what I'm going to do is I'm going to make it molar, like this big M, so I can concentration per second negative 1, that's what it has to be. And then whatever K is, and then I know that the units for H2 H2 is a concentration, right? So it's M, that's what the units are, it's M squared, right? And O2 is also concentration, that's just M. So I end up with M s to the negative 1 is equal to K M cubed. And then what I have to do is solve for K, I divide through by M cubed, I get M s to the negative 1 over M cubed, which is equal to, because I cancel out the M's over there, I end up with, s to the negative 1 over m squared, which you can just rewrite as m to the negative 2 s to the negative 1. And that's how you find it. And then if you want to rewrite it properly in the mole dm negative 3 form, you do moles to the power of negative 2 dm to the power of 6 s to negative 1. Those are the units for K, okay? You should be comfortable doing this for any expression you get, because, I mean, it's not always the same, because you don't always have the same reactants on the right hand side over here. You don't always have m squared and then m. You can also have m cubed, m to the power 4, m to the power whatever, you know, whatever it is, right? Okay, rules for rate expression. Must be in RDS, cannot be a solid, cannot be a catalyst. Alright, yeah, there it is. So must be in the rate expression, must be a solid, cannot be. It can also not be a intermediate, right? So, oh, you wanted me to go back? Okay, give me a minute. Sorry about that. Okay, I hope that's long enough. I can't tell because... Okay. I hope that was long enough. I'm moving on. I will attempt to write clearer, although I am not the best at writing clear. And I'll try and wait for a little longer. Yeah. So where was I? What was I saying? So there's a few different types of things in a reaction. You can have the actual reactants, you can have intermediates, and you can have products, and you can have a catalyst. So those are the 4 different types of things you can have. And in any topic 6 and 7 question, they can ask you about these 4 things. These are really important. So the reactants are whatever are initially being reacted. The products are whatever the final products are, right? The intermediates, right, are whatever is being used in the steps that aren't reactants and they aren't products, right? They're just these things that show up and they go away, but you never actually see them in the reaction. And then the catalyst, right, is something that isn't that's in it, and then it just like it's used up at the start. So you add it at the start, right? But then it gets produced at the end as well, right? So it participated in all the reactions, but you put it in and it came out the same way as it was before. All right. That's what the catalyst, and it's different from an intermediate, because the intermediate, you didn't put it in, it just popped up and then disappeared on its own. No, catalyst got used up and then produced at the end again. Right? These are the few different things you got to remember. So yeah, rate determining step, rate constant. I talked about the units. The reaction mechanism. I'm not sure what I mean by that, but I think I must have covered it over here because I can't remember anything else that was here. Half-life. Half-life is a little bit of an interesting concept. It's not necessary because I've never seen half-life being brought up randomly. But half-life is just how long it takes for the reaction to go halfway. But in all my time doing questions, it's never come up as like an important thing. I'm going to explain Arrhenius. Actually, I'm going to explain order of reactants first, and then I'll explain Arrhenius. So the order also matters quite a lot, because what you need to be able to do is determine the order of which reactions are like determined. So, for example, with the production of water,
where you have two hydrogen molecules plus an oxygen molecule gives you two water molecules. The reaction is actually second order with respect to hydrogen because there's a coefficient of 2 in front. And it's first order for oxygen because there's a coefficient of 1 in front. However, that specific reaction is a little special because that's exactly what the actual rate determining step is, but that's not always the case. Usually, the only time you can actually use this is if you're basing it off of two things: either one, a rate determining step, or two, a equilibrium step, or something like that, right? So you need to make sure that you can't just randomly pick out order from coefficients in any reaction. It has to be a rate determining step or an equilibrium reaction. And then the best way to actually figure it out, and the most common way they will ask you to figure it out, is by using a table or like a table in your in the test itself. And so they'll give you like a couple of different like combinations of concentrations of different reactants. And what they'll ask you to do is they'll ask you to find out what order it is with respect to different reactants. So what you need to see is how does the rate of a reaction change when you like double or triple or like or keep or change the actual concentration of the reactant, right? So for example, if you have H2 and O2, right? If you keep the oxygen concentration the same and you double the hydrogen concentration, the rate of the reaction would multiply by 4, right? That means that it doesn't just double by double, it actually goes by 4, which means that you actually have it's actually squaring, which means it's second order, right? You can also have first order, right, which is when it just doubles straight up, and then you can have zeroth order where it doesn't change it at all, right? And if it's zeroth order, it doesn't even show up in the actual rate of reaction. Okay, let me have a look. Catalyst does affect the rate, and I don't see why it's neglected when establishing a rate expression. No, it affects the rate. Yes, it does. It does. However, it doesn't affect it doesn't come in as a concentration value. It affects the K because there's a constant, remember? So because there's a constant, it increases the rate of reaction. However, it doesn't increase the rate of reaction by literally adding like another term for the catalyst concentration. Instead, it affects the actual K value. But again, you're not tested on that, so don't worry about it. Okay, you're not tested on like the specifics or details of how that happens. So that was just referring to what was happening in the chat. Yeah, exactly. God of Platinum's got it right. Again, so yeah, exactly. Alex M. That's exactly the ones that I'm talking about. We've all seen them. So yeah, those are determined experimentally from those. The order of the rate. You know what? I'm gonna draw it on the table on my whiteboard so that it's easier for you guys to understand. Let me pick okay, I'm gonna make a random reaction. Trust me, this is the actual reactants and stuff could be entirely wrong. Okay, I'm just doing it I'm just picking up something random. I'm gonna use C2H4 plus H2 to give me C2H6. So that's the hydrogenation of ethene. But I'm not, whatever order, rate, reaction stuff I'm doing, do not take it seriously. I don't know if it's correct. But here it goes, okay? It's probably wrong, actually. It's definitely wrong, but this is just for the sake of example. Okay, so I'm just going to put some random values in here. Okay, so to assume that they're all M, so just, right. Okay. So here's what I'm gonna have. I'm gonna check. I'll just keep repeatedly looking back here. Oh my God, so many chats. Okay. Determining reaction order question. They keep on the reactant.
Make your own extra order, compare the reaction rates. Make your own extra row. I'm just thinking about what that means. 1 minute. If you pop that in the Discord chat, can you just ping me there? But let me think. I can see how that would work. Okay, but that's not what they expect you to do. I've never done a question with that. All the questions I've done have been from the past papers. I've done every paper from 2016 to 2018, right? I'm sure as hell if they haven't put one of those, right, in all of those papers. And by the way, for each of those years, there's 3 papers, right? There's a TZ1, TZ2, and a November paper, right? They didn't put it in all 9 of those papers, right? I severely doubt that they're ever going to add a question like that, because I don't even think that's in the subject guide. That is not true. If a textbook has it, it's because the textbook just wants you to do a little bit extra. But I mean, if you could get me a past paper question that has that, I'm all for it. But if you're giving me a textbook question, I wouldn't recommend even studying for that, because that's not going to come up. There's no way. I've never seen that happen. Back to the actual explanation for someone who was asking. So the way that I analyze this, first looking at it, right, is let's say this. So here's the first question they ask you is order of C2H4. Right? They want to find the order of C2H4. The way that I do it, right, is the first thing I think of is I need to analyze C2H4. So I need to figure out when C2H4 is changing, how is the rate changing? But what I need to make sure is that the H2, right, the other one, is constant. So I realized that over here, H2 is constant, 3 and 3 is the same. But here, C2H4 is changing. So these two reaction pathways, combinations, are what I'm interested in right now. So when the C2H4 doubles, because it goes from 2 to 4, it doubles, right? The rate, so this goes by two, the rate goes by 4, right? Which means that it's second order, right? Because when I double, it doesn't just double, it actually goes by 4. So it's actually a square of the double, right? So it actually goes up by 4. So what I would figure out is that the order of this reaction with respect to C2H4 is 2, right? But then afterwards, right, after that, they'll also ask me a question, okay, what's the order with respect to H2, right? So order of H2, right? And if I'm finding the order of H2, I need to find when C2H4 is constant, so I'll use these two, right? These multiply by 3, the H2 concentration. The rate also multiplies by 3. That means it's ordered by 1, right? Because the concentration increase, the rate increased by the same amount. That's 1. And then they'll ask you, find me the rate expression. They'll ask you, find the rate expression, right? And then the rate expression is R is equal to K. Because it's second order with C2H4, put squared, and then it's first order with H2, so I just put a 1. That's the same thing as just getting rid of the 1, because it's just this, right? The last thing they could ask you actually is they could ask you to calculate what the constant is, right? If they ask you to calculate what the constant is, right, this is really simple. Pick any one of the reactions you want. I'm going to pick the first one, right? The rate of reaction is 5. The K is just whatever K is. The concentration of this one is 2. That's 2 squared. And then the H2 is 1, so that's just 1. So what I end up with is 5 is equal to K times 4, right? So K is equal to 5 over 4, right? They might also ask you for the units of that, but I went over that, whatever that would be earlier. But yeah, so here's how you would also find the rate constant from this equation here. I can wait on this any longer if anybody likes. So I just saw something in the chat saying that isn't the order of H2 3? No, it's not true. Because when I multiply the concentration of H2 by 3, right, from 1 to 3, that's by 3, the rate also increases by 3, right? So it's order H2. It would be third order, right? If I multiplied 1 to 3, I multiplied by 3, but then the rate increased by 27, right? But no, it just increases by 3. So yeah, that's the order of the reactions. Also, you're only tested on first and second order. I've never seen a third order question. So if you end up with something where it says, where you find out that it's third order, you're doing something else wrong, because that's not possible. Let me see what's happening here. Again, we can refer back to the study guide, and then we'll see. Let me see how many 20 concurrent years. All right. Okay, let's keep going. Yeah. So on the slow step, but yeah, we're good. We're good with this stuff. Finally, Arrhenius equation, right? This is an equation which straight up just this is in the data booklet, right? So you should know what all of these are because it's in the data booklet. The equations itself are in the data booklet, but you don't. I don't think what each of these things means is in the data booklet, but separately they are. So EA, easy to understand what that is, activation energy, straight up. The R, that's actually in your data booklet. It's a gas constant, so you should if you forget what R is, just check your constants. You'll find R. T is the temperature in Kelvin. E is the exponential. You know how E, just E. And A, right, is the pre-exponential factor. That's your Arrhenius, or the Arrhenius factor, which we were discussing earlier. So each of these things takes into account different things, right? So the T actually takes into account for how the temperature might change the rate of reaction. So in general, what the K, if you're increasing K, the rate of the reaction is going to increase, right? Because you have R is equal to K, whatever, you know. So if you increase K, the rate of reaction is going to go up. So if your temperature, right, is going up, right, that whole fraction over there is getting smaller, right? Which means that it's e to the negative something smaller, which in general will increase K. So that's what speeds up the reaction. The complexity is taken into account into A, right? They'll never ask you like whether A goes up or down or what happens to A, but all you need to know is that the complexity of the collision is all dependent upon A. The activation energy also adds up, so if the activation energy is reduced, right, then again the exponential itself, that's its value is going to increase, because e to the negative EA over RT is just the same as 1 over e to the power of EA over RT. And then the other way you can represent the same thing is ln K is equal to negative EA over RT plus ln A. The reason we use this alternative way to represent the equation is because it helps us graph the equation so that we can figure out the activation energy of a reaction, right? And the reason it helps us do that, right, is if you think about what it looks like, right, it looks very similar to a y equals to mx plus b reaction, right? Where ln K is y, and then the x is actually 1 over t, right? And because the activation energy of a reaction and the gas constant reaction are always constants, right? So the only things changing here, if you are changing anything, is K and T. So ln K will change. Okay, so earlier we actually discussed that the complexity of a collision is actually will affect the rate of reaction, but it has to be involved somewhere, right? Like it can't just randomly be popped up somewhere. So the place where it is relevant is here. So the K it's in A. So the Arrhenius factor, the pre-exponential factor, the complexity gets taken into account over there. Temperature gets taken into account at T, activation energy gets taken into account into activation energy, but A is dependent on the complexity. Again, so back to our equation. ln K is roughly the Y value. 1 over T is whatever X would be, and our slope would be negative EA over R, right? Negative EA over R. And our y-intercept would be ln A. That's the plus B in the end. And that's a simple way to have the line. So that's how I just visualize it. And what you would do is you'd have to graph ln K on the y-axis, and you would have to graph 1 over T on the x-axis, right? And then another representation, which I see, is ln K2 over 2 is equal to, this is just another way to represent, to find out what the activation energy could possibly be if you have two different T values or something like that. In general, I don't think I've ever used that second equation often. I mean, it may have come up in a question like once or twice, but from everything I've done so far, it hasn't come up often. There's probably usually another way to do it, but again, that's an equation you should remember. K1 and T1 refer to like some possible combination of temperature, and K2 and T2 refer to some other possible combination. And the goal is usually to find out what the activation energy is, and that's how you would do it. So yeah, that's the Arrhenius equation stuff. Some more math that you're gonna have over here. The first order, second order reactions. This is usually a paper 1 type of thing, which usually comes up. I'm going to pop up with the whiteboard for a second for this one. And hopefully I don't mess this up. When a reaction is first order, with respect to any reactant, right? So let's say this is the concentration of that reactant, right? This is the concentration of the reaction. This is the time the reaction is progressing. If it is first order with respect to that reactant, the concentration as it goes with time will go down like this. Let me think. Like that. Right, and as time goes to infinity, the concentration will reduce entirely. It starts reducing quite quickly because the rate of the reaction is high, but as the product gets used up, it reduces, right? However, if the same thing was second order, all you would have is a slightly steeper graph, right? A slightly steeper graph. I'm gonna open this up right here. The slope is negative EA over R, not negative EA over RT. Okay, that 1 over T, right, is actually something you put on your x-axis. It's just negative EA over R. Okay, HSN is incorrect. A second order, and then you can also have zero order, right, where it doesn't affect it at all. So if it's zeroth order, the concentration would go just like that. That's it. All right. So that this is the graph for the concentration of reactant, zeroth order, first order, and second order. Another interesting thing you could have is the rate versus the concentration. So the rate versus the concentration. So that's the rate of the reaction, depending on what the concentration of a certain product is when it starts off. So if it's zero order, right, that means that the concentration of this doesn't affect the rate at all, right? So in that case, for every concentration, the rate is the same. So it's just a flat line, right? If it's first order, right? If the concentration, if it's dependent on the concentration, then as the concentration increases, the rate also increases proportionally, right? So it increases like that. It's important to remember it crosses the origin, right? Because if you have concentration 0, then you're going to have an increase. You're going to have no rate of reaction because R is equal to K times whatever that concentration is. And if that concentration is 0, there won't be any reaction. And then finally, you have a second order. You have the rate and you have the concentration. In this case, the rate increases faster with higher concentration, so it'll look like that, right? So these are the important graphs you need to know. I can let you guys copy that down for a little bit, I guess. I'll just wait for a minute. That's okay, HSN. This is HL. Anything related to like these orders of reactions is all HL. Okay, I'm gonna move on now. Oh, we're on topic 7 now. I will start the topic 7 at 8:20. In the meantime, I will go drink water. Top 7 session. Okay, I'm back. Let me see what these questions are. Why is it that if you halve the concentration of your reactant but double the volume, the graph for its product over time changes? What is that referring to? I don't know what that means. I don't know what graph that's referring to either. You can pop into chat and talk to me about it. Oh, I see what you're saying. Okay. Yeah. So there's less frequent collisions because the concentration. So if you have the concentration double the volume, there's the same number of moles, but all of this time, rates of reaction and rate expressions aren't dependent on moles. No one cares how much of it you have. It only matters how much of it you have in a certain volume. So if you have the concentration, it doesn't matter how much you double or triple or quadruple the volume. You're going to still have the same initial reaction rate. However, what could increase, right, is the final amount of product you have in the end. That could increase, right? But what doesn't increase is the actual initial rate of the reaction. Okay, so I'm set to start. Casey, you can just join the session by like joining YouTube. I mean, if you can like watch YouTube, you can join this session. So. Okay, I'm gonna continue with topic 7 now. Hopefully, all the SLs are back. Let's see what the. Okay, so Shri Bacha, the volume affects the rate because if you increase the volume, then your concentration is going to reduce. Yeah, but either way, only concentration affects it, right? And like, I mean, obviously other things like catalysts and things like that, or temperature, but concentration affects it mainly because if you change the but yeah, and again, volume's connected. If you reduce the volume of something without changing the concentration, like you have the same number of moles of a substance with higher volume, that means you're going to have a lower concentration, so you're going to have a lower rate of reaction. But you know what would have the same rate of reaction? If I doubled the volume, right? But I also doubled the concentration, right? Um, oh no. If I doubled the volume, but also doubled the moles of substance in in the solution, that would help. Yeah, so that's more specific. Everything here. Okay. Let's just continue then. Topic 7 time. You're confused now? Oh, okay. So, okay. Here's the best way to do this. So concentration is equal to moles over volume, right? If you increase the volume, right? If you increase the volume, then you're going to decrease the concentration, right? Because the denominator is increasing in value. So yeah, volume does reduce the concentration. However, you can avoid that. You could avoid that. The way you would avoid that, right, is if say you double the volume, but at the same time you double the moles in the solution, then you'd have the same concentration. Then there's no difference, right? But I mean, and in the same way, right? You could half the volume, right? But if you half the volume with the same number of moles of substance, it does the same thing, you know. So yeah, that's kind of how that works. And this goes back to different ways that a rate of reaction that different ways that rates of reaction can be impacted. Yeah, topic 7, SL stuff first. So equilibrium is a point where the forward reaction and the reverse reaction are equal to one another. That's how you would define equilibrium. So if they ask you like what does equilibrium mean, it means that the forward and the reverse reaction are equal and opposite. You know that they're both the same speed, right? And connected to that, right? If your catalyst, actually, 1 minute, let me think about this. Lishat Leach principle HL, sorry. The equilibrium constant is that in SL? Can someone confirm that for me? Anyways, I'll go to like the actual. I think it is. Yeah, it is. So forward and reverse reactions are the same both ways. This is actually why catalysts do not affect the equilibrium rate, because what catalysts do is that they provide a faster energy pathway, but they provide a faster energy pathway for the forward reaction, but they also provide a faster energy pathway for the reverse reaction. So it works both ways anyways. So it ends up being cancels out anyways, and then you end up with the same equilibrium point. So catalysts do not affect it at all. Why am I looking at the rate determining step here? I don't know why. And then the only thing that can actually change. So now let's look at the equilibrium constant and what it is. Let's pop open the equilibrium constant. So the equilibrium constant for any reaction. So I'm just gonna draw my trusty reaction. Right. The equilibrium constant for this reaction is you take. Oh, sorry, 1 minute. Right. Equilibrium. You take whatever's on the right, the product, you put it on the top, that's your numerator, and you put in the bottom, you put your letters like that, you put O2 like that. Oh no, O2 doesn't have a square on it, sorry. Yes, you just put the coefficients. It's quite simple, straightforward. And yeah, this is how you end up. This is how it ends up going. This is actually a little bad because usually you wouldn't put H2O, right? Because if you have like an aqueous solution, you wouldn't do it. But in this situation, I guess you kind of would. This is just generally a bad example for a equilibrium reaction, but I just chose it because I mean it's just the one I was going to use. This is just the first one that came to my mind. But this is how you would create an equilibrium constant. What actually was interesting, right, is this equilibrium constant is completely unaffected by changes in pressure, by changes in concentration, or anything, right? Because if you have a change in concentration, right, in any time or when things are at equilibrium, the equilibrium will be restored on its own. And it will not, and concentration won't affect it. Same thing with pressure. If you increase the pressure or something, again, automatically each of the reactants and products and all the possible things that are relevant there, they'll all cancel each other out and make sure the equilibrium constant is exactly the same. The only thing that can affect the equilibrium constant is temperature. So if you change the temperature, then the equilibrium constant changes. And in general, the equilibrium constant's value is kind of important because what it tells us is whether the products are more favored or whether the reactants are more favored, right? Because if the equilibrium constant number is greater than 1, right, that means the numerator is larger than the denominator. So that indicates that there's more of the products than there are of the reactants. But if the equilibrium constant is less than 1, that indicates that the denominator is larger than the numerator, which indicates there are more reactants than products. And the reason why only temperature affects it as a temperature dependency is actually a HL topic, a HL part of it, and it's because if you remember what the Gibbs free energy equation is, it's the delta G. So Gibbs free energy is directly related to the rates of reaction. It's directly related to K and the equilibrium constant, right? And so the Gibbs free energy is actually it's a good measure of understanding what the equilibrium constant is. It's actually another way to represent the value, numerically speaking. Because all it is just some calculations with Kc to get it. So the Gibbs free energy is related by delta H minus T delta S. Delta S, the entropy, usually stays the same. Delta H, the enthalpy, usually stays the same. The T is the one that changes delta G, and that's why it changes Kc. Otherwise, every other thing just cannot affect the equilibrium constant. It cannot affect Kc. All right. Yeah, so the equilibrium will shift to the side where there's less stuff. But it's self-fixing. It always makes sure the equilibrium constant stays the same. It'll always fix itself. Don't question it, right? Temperature is the only thing that affects equilibrium constants. That is the word of God. Okay, just whatever. The other interesting thing is you gotta try and remember is reaction quotient, right? So so this actually relates to a couple things. I don't mean to pop them on a whiteboard instead. So we could have so the reaction quotient, what that tells you is whether your reaction is going to head towards equilibrium or not. So here's what I'm going to do. I'm going to have a reaction. I'm going to pop into another one of my reactions I keep using where it's completely irrelevant and probably not used correctly. C2H6. And let's say that the Kc for this reaction is 5. All right, it's 5. Again, okay, there's another important thing. Kc has no units. Remember, equilibrium constant, it's a ratio, practically speaking. Which is also why we take the ln of it when we do one of the equations. That's again HL stuff, but yeah. So you have Kc, right? It's a good 5. But let's come in and let's say we're putting in C2H4 and putting H2 in a container, right? And we put in C2H4 of concentration 1 moles dm negative 3. We put H2 of concentration 2 moles dm negative 3, right? What concentration of C2H, what's going to happen to this reaction over here? Like what's going to happen to the reaction? And the best way to actually figure out what's going to, actually, you know what? Let me do one more thing as well. So what's going to happen to this reaction over here? If we have 1 moles of C2H4 and 2 moles of H2, and let's say we have 3 moles dm negative 3 of C2H6. We put all of this in a bag. Which way is the equilibrium going to go?
Are we going to get more C2H4H2 or are we going to get more C2H6? The way we do is actually we look at the reaction quotient. So first we actually look at what the equilibrium constant expression is. So let's look at what Kc is for this reaction. It's C2H6 on the top, right, like so. And it's C2H4 on the bottom, like so. And you have H2 on the bottom, like so. So this is how you would have it. And then what you do is you actually calculate with the reaction quotient, like what would it look like if we just took whatever we have right now and put it in as it is, right? We'd have 3 over here, we'd have 1, we'd have times 2, so that would give me 1.5. So Q is 1.5. What does that mean? That means that we have more products, right? We have more products than reactants, but not by a lot, right? Like it's 1.5, it's a little above 1, right? But let's look at what our Kc is. Our Kc says 5, right? That means that we have 5 times as much concentration of the products than the reactants, right? We have significantly more product than reactant. But the Q is only 1.5, which means that if the Q is significantly less than the Kc, right, that means that the reaction is going to go towards the right because it has to become larger so it can allow more product so that the Kc value can become bigger. And then if we have a larger value for Q, then we'll end up with a larger Q value which approaches Kc, so that we can actually have the correct equilibrium for this thing. So in reality, for this equation, for these conditions, what I put in, the 1 mole C2H4, 2 moles H2, and 3 moles C2H6, is actually not at equilibrium, right? It's going to go towards equilibrium, and there's going to be a lot more C2H6 being formed at the end of it, right? So that's another thing you got to remember. So you need to remember, so it's really easy to just write Q is equal to this. They could ask you in a question, they could ask you, this is what the Kc is, which way is the reaction can go, right? You calculate the Q, you compare it to Kc, you make a judgment on it, and that's how you do it, all right? Another thing which this actually leads into is ice diagrams, right? So ice diagrams. So when you're given an ice diagram, this is the most common way they do it, right? They'll give you 1 mole DM cubed C2H4, 2 moles of H2, right? But then they'll tell you at the end of it, right? At the end of all of this, we ended up with only 1 mole of C2H6. 1 mole of C2H6, right? 1 mole DM-3, sorry. DM-3. 1 molar C2H6, right? That's what we ended up with, right? So what you have to do right now is think about the ice of this equation. So you got to think about the initial, how much was there initially, how much was the change, and how much is at the end of the reaction. So the initial for C2H4 is 1, for H2 it's 2, and this is 0, right? This becomes 1. Right? So actually no, sorry. But at the end, C2H6 is 1, right? And what is the change in that? That means there's a +1 change right over there, right? So this is a plus, and this again now we use our molar ratios to figure out. So if there's a +1 in C2H6, because they all have the same coefficients, C2H4 is also going to be a -1, right? And H2 is also going to be a -1. So you're left up with, at the end, you're going to be left up with 1 minus 1 is 0, and 2 minus 1 is 1. And this is what your final looks like, right? And then you can say, oh, so if you ended up with C2H6 of 1 at the end, that means that C2H4 had concentration 0, and H2 had concentration 1. Yeah. But that's a relatively simple one. Let me see. Equilibrium constant and the position of equilibrium. Let me think. Yeah, so, okay, I'm going to try and answer these questions. So, if Kc is bigger than Q, the equilibrium shifts right. Yep, that's correct. If Kc is smaller than Q, the equilibrium shifts left. You can just remember that. But alternatively, what you can remember, right, is that if Kc is bigger than Q, that means that for Kc, right, there's a lot more product. And for Q, there's not that much product, right? Because the bigger your equilibrium, whatever these equilibrium constant values get, the more product you're getting, right? So that means whatever your Kc is, it needs to have more product. But whatever your Q is, doesn't have enough of that product. So it has to shift to the right to get more of that product. If Kc is less than Q, right, that means that your reactants, you need to have more reactants so that you can reduce, and then you have to create more reactants so it goes position to the left. The difference between equilibrium constant and the position of equilibrium is that they're entirely different concepts, right? Equilibrium constant is telling you how much products you have versus how much reactants you have, generally speaking, right? The position of the equilibrium changes depending on different things you have in your, the different things are changing, and that can change the Kc. So it can actually, if the position of equilibrium moves to the left, that means you have more reactants, right? So if you have more reactants, that means that your Kc is going to reduce in value. If you have more product, then your Kc is going to increase in value. But again, the Kc itself only changes for temperature-related things. If your position of equilibrium changes for for pressure or for volume or concentration, it does not change the actual Kc value. That's kind of what it is. Yeah, God of Platinum makes sense. Kc is a simp for Q is a simp for Kc. That's what it is. Generally speaking. Okay, let's continue. I think I went over everything. This is everything I think that's SL. That's everything that's SL. So we're going back into the HL stuff. 7 is short. That's very short. Yeah, 7 is quite short. So this is gonna be quick. So changing equilibrium, the Chatelier principle. Everything will always try and resist change, right? So, for example, if you have a endothermic reaction, right, and a reaction that needs energy to happen, right? If you increase the temperature, right, they will start producing more products, right? So that it uses that extra energy, right, which is provided by the higher temperature, in order to forward the reaction and reduce the temperature again. But then, right, if you reduce the temperature, right, what it's going to try and do is it's going to try and increase the temperature again to resist that change, right? And it is going to favor the reverse reaction, which is exothermic, right? And by doing that, it actually goes against whatever change is occurring towards it, right? And the only way to do this is to logic it out, right? And the same thing goes for pressure, right? If your pressure is increasing, right, it wants to try and make sure that it has less gaseous molecules. So for example, with the case of production of steam, for example, right, if you have H2 gas, you have two hydrogen molecules, right, and one oxygen molecule to provide two gaseous water molecules at the end, right? That's what it has to produce. On the left-hand side, you have 3 moles of gas. On the right-hand side, you have 2 moles of gas, right? So if you increase the pressure, they want to try and do the forward reaction, so it reduces the moles of gas, right? Because it's trying to resist the increase in pressure by reducing the pressure again. So Le Chatelier's principle is always trying to do the opposite of what is being done to it. It's always trying to resist change. So it could do that for pressure, for temperature, and for temperature you can figure it out by understanding whether it's endothermic or exothermic. It could also do it for pressure, and the way you know for pressure is how many moles of gas are on either side, and it'll push forward or reverse depending on which one it is. I think temperature and pressure are the only ones that are there that are important. I think volume, not so much. Volume is closely related to closely related to pressure, so that's not as big of a concern as well.
Okay. The final thing is equilibrium movement for HL. The Gibbs free energy in the K. So there's like an equation written in your data booklet to convert from K to Gibbs free energy. You just have to know that. And I kind of explained how the Gibbs free energy and the K are related a little earlier. But there's that equation in your data booklet that literally converts from K to Gibbs free energy. It's like the simplest one ever. There's like definitely going to be 1 or 2 marks in the paper where it's just like, here's what K is, tell us what the Gibbs free energy is. That's all. That's how you do it. When you have a very large K value, a K value that's larger than 1 in general, what you'll end up with is more product, right? That means the Gibbs free energy is going to be relatively negative. If you have much smaller than 1 K value, then your Gibbs free energy is going to be positive, which is why the reactants are more favored than the products. And that's what the connection is. Oh, yes, sorry. Sribacha is correct. The changing equilibrium for Le Chatelier's principle can also have a concentration. Again, that's when it's quite simple, because if you reduce the concentration of one of the sides, to try and restore equilibrium, Le Chatelier's principle, by Le Chatelier's principle, it will go towards whatever side the concentration was reduced. Yep. So that's 3 things: pressure, temperature, and concentration. Yep. And then I went over equilibrium movement. I think that's it. I think that's all there is. That's all there is to all of this. Sorry. Does anyone have any final questions? Yeah, okay. I'll clarify the relationship right now. Give me a minute. I'll do it on the whiteboard. Okay. Okay. Sorry. Okay, so if your K is less than 1, right, that means that your Gibbs free energy is going to be greater than 0. Why? Because when Gibbs free energy is greater than 0, that means the reverse reaction is favored, right? That means the forward reaction is not going to happen. And when K is less than 1, that means it's reactant favored, right? Because the denominator is larger than the numerator. That's the connection. When K is greater than 1, G is less than 0. Same thing, forward reaction is favored and product favored. This is the important reaction you have. And this is directly related to actually what the thing is. So if I remember what the equation is, it's actually delta G is equal to negative ln K or something like that, you know? Actually, this is, I think it's negative RT ln K or something like that. I think it's that. I think from the top of my head. And if you notice, if K is less than 1, right, that means that the value of ln is negative, right? Which means that if the value of ln is negative, then negative times negative is a positive. That's how you get a positive Gibbs free energy. If K is greater than 1, that means that your ln value is positive, which results in a overall negative Gibbs free energy. So yeah, that's how that one works. Okay. I think that's all. Okay, cool. I think that should be everything then. Okay, you guys can read Batman's explanation here, but good night. I'm done. Goodbye.